And I'm representing Unibap, and Unibap is bringing cloud technology up on orbit to the satellite and extending the possibility of executing containerized applications on orbit on your satellite. We are a dedicated, I would say, payload data processing technology. We don't replace any onboard computers, etc., but could give input to control of things. But it's purely to bring in sensor data, do cloud-based computing using containerized applications, using Docker containers and gRPC calls, and handle the data on orbit as well as queuing up and download data to the ground segment. So what we allow then would be to have data preparation and meta tagging on orbit using AI and machine learning. And we can also create a spectra of very low latency data products. The solution itself is an x86-based heterogeneous architecture, so it's a lot of heritage software that actually can be deployed on orbit to support your missions. And this is a kind of a schematic to show the different aspects of cloud-based computing in space. Where we, for instance, may have a satellite using Space Cloud. You find something of interest in the image or in the data stream captured by sensors on board. Could be optical sensors, could be RF-based sensors or whatever. And then that data either could just be prepared and sort of filter out anything of non-relevance, and then you queue up the data to be downloaded. Omitting all the data that would be, let's say, fully clouded coverage, MTC or whatever, that would be of no relevance. Or you could actually get a very, let's say, low latency data product already manufactured or produced on the satellite using a processing pipeline. And that information could be forwarded using inter-satellite communication, for instance, or just queued up as high prioritized download to the next satellite pass and be readily available for the end user. Another scenario we also heard earlier about would be introducing autonomous operation and autonomous mission or parts of the mission, I would say. One way would be to autonomous task the next satellite in line, for instance, of something, an event of interest, to sort of provide a tipping and queuing capability where satellites could continuously detect and monitor something of interest without the need of doing processing on ground beforehand and then reschedule satellites after a certain amount of hours to sort of take care of that in next passes, etc. And this would be, of course, very much more important if you talk about lunar mission or mission on Mars or wherever it's going to be very low latency in the communication between an operator and the satellite. The other aspect of this would be the increasing amount of spatial and spectral resolution on sensors, for instance. I mean, it's a huge amount of data that they can produce with high frequency. And in order to download all that raw data and do the processing on ground, if you have a larger constellation of satellites, it suddenly becomes a very cumbersome task. Of course, the ground station providers would be very happy about that because it would be requiring a lot of communication. But on the other hand, we think a lot of things could be handled on satellite with a smart way of distributing or segment your compute tasks. You could actually find yourself in a situation where you have a much lower cost for your mission and or you have data products at a very much lower latency to your end users. So what we provide there to enable this would be a spaceflight on computers and the associated ground equipment for development and an operating system and framework SDK for the developers. And then we have a number of different application partners and the growing ecosystem of different applications where already let's say pre-tested, pre-configured applications could be used in the processing pipeline on orbit to provide different compute tasks. We'll talk more about that. The software stack is essentially a Linux distribution that is based on Ubuntu. It's a frozen one where we have some tweaks to the kernel and some specifics to the drivers that that enable this to work seamlessly on our in-flight hardware. On top of that, we have the Space Cloud framework that allows you to have these cloud computing capabilities to execute code and applications in containers on the satellite, and then a number of different applications or libraries of different applications. And here we really think this is a key enabler for future developers to actually come from traditional software development on ground for terrestrial applications, could be image processing programs or other types of applications that you would like to port to the space platform. And that could fairly straightforward, easily be done here using this framework. This is an example where we are right now flying on the Orbit Dauntless David Ion Wild Drive mission. And just as an example, within 4 months from start, from actually where we signed, we're in agreement of what to do, delivery of hardware to the satellite and performing integration of up to 23 different applications that has been running on the satellite. We have been sort of showing and demonstrating that it's really possible to have a very rapid deployment of software, quite advanced software on board the satellite. And just to showcase the small form factor of half a U sized computer is called IX5100 in this case, and we are also in development of next generation of onboard processing unit, having more than 20 times more capability, up to 50 times more capable than the existing one. So that is in process. So this is an example where we have actually ported the full software suite of Envy. Envy IDL has been sort of put into the Space Cloud as a application, meaning that the full software suite is there, and one could write a small application of 5 to 10 megabytes of size to upload and orchestrate that to perform on-orbit processing of images captured by the sensor. And Envy is having a quite long heritage of as a software for terrestrial computing. This is an example of what we did, and it's a 100 square kilometer satellite multispectral image from WorldView 3. This was canned data. We did not have the sensor on board on this mission. Obviously not the sensor capable of 30 centimeters of resolution. But this image, the task was to find the in-flight, mid-flight airplane in this image, and running algorithms to find that needle in the haystack, as it was called, the challenge. And together with Saroniasat, one of our partners, they developed the algorithm for detecting airplanes in mid-air flight, and this is what can be achieved within 10 seconds on an IX5100. Just to give you an example, what can be achieved on orbit. And I think with that, I would kind of stop my presentation here now, and maybe have a few discussion points later on, and happy to answer any questions.